two more examples of proof by induction. We're going to do one that involves a summation this time. And the rest of them that we've been looking at so far have just been the written out series. This time what we're going to do is we're going to write the explicit form of the series, or in this case, the sequence that coincides with the series. And we're going to say that for all n in the integers, as long as n is greater than 1, that the sum of I equals 1 to n of I cubed is n squared, n plus 1 squared divided by 4. First step, basis. Now, let's let n be equal to 2, just so I can illustrate. Remember, we're starting at 1 here. All right, so let's let n equal 2 by substitution. This is going to say that the series I equals 1 to 2, all right, since n is equal to 2, of I cubed is going to be equal to 2 squared, 2 plus 1 squared divided by 4, just substituting right into the right-hand side. And this is just going to become, so we know that this is just going to be 1 cubed, this should be I, by the way. This is going to be 1 cube plus 2 cube, that's on this left-hand side. And then on the right-hand side, we're going to have 4 times, and then this is going to be 3 squared, which is 9 over 4. And the good news is those 4's cancel out. 1 cubed plus 2 cubed is going to be 9 and equals 9. And we're good. All right, so the basis step holds. Okay, so thus, the basis step holds, or seems to hold, or whatever. So seems to hold for small values of n. Right. Now let's assume that the basis step holds for all n equals k. So now assume that the formula holds for all n equals k, where k is an integer. Okay, thus, we are going to say, and all we're going to do is just replace all the n's in our formula with k instead. All right, so that's going to mean that the series I equals 1 to k of I cubed is going to be equal to k squared, k plus 1 squared divided by 4. And again, just substituting directly into our formula that we started with. Okay, so that's the first two steps. Those are pretty easy. Now, the tough part for this one is where you're going to substitute n equals k plus 1. And I'm going to show you the trick for that one, especially with a series, because we haven't done one yet. So let's let n be equal to k plus 1. Okay, by substitution, we're going to say that the series I equals 1 to k plus 1 of I cubed is going to be equal to, it's going to get a little ugly here, k plus 1 quantity squared, k plus 1 quantity squared over 4. And of course, if you want to, you can go ahead and just make that k plus 2 squared, but just to make sure it's explicit, that's what we have at this point. Now here's the trick. What we're going to do is we're going to break off the k plus 1th term in this series, all right? So we're going to plug k plus 1 in back for I, all right? So we're going to split off k plus 1, and we're not doing induction yet. This is just summation rules. So this is going to be k plus 1 cubed, and we're going to be left with I equals 1 to k of I cubed. So all we did was we just plugged in k plus 1, and that took us back to k, right? And of course, if you don't believe me, just go ahead and try it for some real numbers to justify it for yourself, right? Now, that's going to be equal on the right-hand side to k plus 1 square, quantity k plus 2 square, all over 4. Now, what's the good news about this? Well, the good news is that, remember we said up here, our inductive hypothesis had a formula for I cubed. It was k squared, k plus 1 squared over 4. And so this is now going to be equal to, oh, by the way, this is by summation rules and computation. Right? And so now we're going to be equal to, by substituting back in, this value or this formula for the summation is going to be k squared, k plus 1 squared over 4. And now we still have this k plus 1 cubed. And that's going to be equal to our right-hand side. All right, so that's by induction. All right, now, just like the previous 3 problems, we're going to get a common denominator. And I think that's pretty obvious at this point. So k squared, k plus 1 squared over 4 plus 4 quantity k plus 1 cube all over 4. Okay, so that's our least common denominator. And I know it's tempting to FOIL this out, okay, but you don't want to FOIL. You always want to try to factor before you do anything else, so that way you don't get these ridiculously long polynomials. I want you to notice that there's a k plus 1 square that's common between the 2 binomials. So let's factor that out. We're going to factor out a k plus 1 square. And what is that going to leave us? Well, that's going to leave us with k squared plus 4, and we've taken 2 of these away, so we're left with 1 all over 4. Okay, and that's still equal to our right-hand side. That's by our greatest common factor. And I think at this point we know what to do. We're going to distribute the 4. So we're going to get k plus 1 squared, k squared plus 4k plus 4 all over 4. And that's going to be just by distribution or multiplication. And we know that we can factor this into k plus 2, k plus 2. And if you want to just jump right to the answer, that's fine. Right? But for those of you that aren't as adept at factoring so quickly, then you could just factor it as basically the 2 binomials. And so that's by factor. And we can actually combine these by using exponent rules, because it's really 1 and 1. So if we add 1 and 1, it's just 2. So this is going to be equal to k plus 1 squared, k plus 2 squared all over 4 is equal to hopefully our right-hand side. And that's just, again, by factoring or exponent rules if you wanted to. All right, if we go all the way up here, k plus 1 squared, k plus 2 squared over 4. And that's exactly what we needed. Okay, so we can say, thus the result holds, or thus the formula holds. For n equals k plus 1. And then finally, we can say by our basis and inductive steps, the formula is valid. And hence, for all n in the integers, I believe n started at 1. Let me go back up here just to verify. N greater than 1, the summation of I cubed. So for n greater than or equal to 1, we can say that the sum of I equals 1 to n of I cubed is indeed equal to n squared, n plus 1 squared over 4. All right, so we've shown 4 of these to be valid. All right, so the good news is now you have a pretty good understanding, hopefully, from watching these as to the techniques necessary to be able to solve these types of, or prove these types of formulas by induction. Right. Now this is a little bit different one, because now we're going to move away from summations and we're going to start taking a look at divisibility. For all n in the integers, if n is greater than or equal to 0, n cubed minus 7n plus 3 is divisible by 3. there's two ways that you could try to attack this problem just by looking at this. You could certainly do division by cases, but we know division by cases is pretty lengthy and we'd have a lot of work to do with that. All right, so let's use mathematical induction. All right, so basis step. Okay, let's let n be equal to 0. All right, let's just use the most basic step that we can. We can use whatever we want, but by substitution, we can say that 0 cubed minus 7 times 0 plus 3 is equal to 3. And we know that 3 divides 3. And remember, we're looking for divisibility, all right? And of course, if you really wanted to, you could say 3 equals 3 times 1, which contains a factor of 3. So by definition of divisibility, this is fine for us because we're just trying to verify the basis step, right? So what can we say? Well, thus, the basis step holds. Well, we could say seems to hold for small values of n. Now we're going to assume that this property holds for all n equals k, where k is in the integers. Thus, what can we say? We can say k cubed minus 7k plus 3 is divisible by 3. And since it's a divisibility problem, we're going to throw in one new step here. And by definition of divisibility, we can say that k cubed minus 7k plus 3 is equal to 3p, where p is an element of the integers. All right. So we're going to hold on to this. This is probably the most important part because this is what we're assuming. Okay, so we're assuming it holds for all n equals k and then the definition of divisibility. All right, now we're going to substitute n equals k plus 1. Excuse me. So let n equal k plus 1. By substitution, we can say that k n squared or n cubed, excuse me. So we're going to say that n cubed minus 7n plus 3 is going to be equal to the quantity of k plus 1 cubed minus 7 quantity k plus 1 plus 3. All right. Now, we are going to FOIL this out. Okay. Usually we try to factor, but in this case, there's nothing to really factor. I mean, we could certainly factor out a k plus 1 from these two terms, but I don't know if that would help us too much. So let's just FOIL out the k plus 1 cubed. Okay, so that's going to be equal to k cubed plus 3k squared plus 3k plus 1. And if you're not sure how to get that, just do this and then FOIL it out. All right, just take my word for it that indeed that is the FOIL for this. We're going to distribute the negative 7 plus 3. All right, and that's just by like terms. Okay, or we could just say by polynomial multiplication. Okay, so what do? We usually combine like terms, all right? But this is one of the things in discrete mathematics where we don't want to combine like terms, all right? And why is that? Well, if we look up top, we have a k cubed, we have a minus 7k, and we have a 3. We have a k cubed, we have a minus 7k, and then we have a plus 3. And all of those are equal to 3p. So let's just use induction and just say that we have 3p from these three terms. Okay, now the rest of the stuff is going to come right down. So we still have the plus 3k squared plus 3k plus 1 minus 7. And that's just by induction. Right? Now we're going to combine like terms, and really there's just computation here. So that's going to be 3p plus 3k squared plus 3k minus 6. Okay, computation, yawn. Right? What are we trying to do? We're trying to show that it's divisible by 3. Well, looks like everything has a factor of 3, so let's factor a 3 out. So we have p times k squared plus k minus 2, and that's just by factoring out a greatest common factor. We know that p is an integer, we know that k is an integer, we know that 2 is an integer, and hence addition, multiplication, subtraction of integers becomes an integer. So we're going to call this 3q, or q is an element of z, by closure. And we're done. We've shown, so hence we can say k plus 1 cubed minus 7k plus 1 plus 3 is equal to 3q, and hence contains a factor of 3, which means it is divisible by 3. Right? And therefore, the result holds for n equals k plus 1. So thus, the statement holds for n equals k plus 1. And finally, by our basis and inductive steps, we can say that for all n in the integers, n greater than or equal to 0, we can say that n cubed minus 7n plus 3 is divisible by 3. All right, just made it. All right, so those are two more examples, one of which was a summation, one of which was a divisibility proof. And we're going to continue with divisibility. And then the last thing we're going to take a look at in this chapter or this section is inequalities by induction.